Today's video, we're going to talk about resonance structures, specifically what happens when you have double or triple bonds between different atoms, and more importantly, this idea of Lewis dot structures. And so when you think of resonance structures, what you're really talking about is this idea of having multiple Lewis dot structures for these specific, I guess you want to call them electron arrangements. And so what you're going to end up having is that for the AP Chem test, you're going to have to figure out how to draw the Lewis dot structures for a lot of the polyatomic ions. And you're going to have to draw all the possible structures with the two-way arrows for those. So here's an example of one where you're going to have to take a look at the resonance structures with bond length and bond energy. So if I ask you right now is what bonds are longer or shorter, what you're going to have to figure out is exactly the bond order for those. And so ozone can be written down as two ways. You have a double bond with the oxygen on the left, and you have a single bond with an oxygen on the right. And the way this usually works is that when you're taking a look at ozone as an example, is you have to take into consideration a couple of things. The first one is because it has an alternating bond, you each are going to have to figure out which one is the official Lewis dot structure. And because in this specific case it can exist as two situations, ozone actually is the average between these two. And so we're talking about the average bond between them. It's going to be the number of effective bonds. It's not going to be 3, but more importantly, it's going to be 1.5. And I'll talk a little bit about how we get that 1.5, but resonance structures usually take the average of those. So if you see yourself in a situation where you're trying to determine what the correct one is, usually it's most likely a resonance structure, and more importantly, you have to take into consideration the bond order. So here's another example of nitrate. So nitrate is NO3 minus with an excess charge with minus, and nitrate exists in 3 forms. NO3 on the left with the double bond is on the first O. The NO with the double bond is on the top oxygen, and finally the N on the far right. In this specific case, nitrate exists in the 3 between those two. So how many bonds you actually get here is going to be 1.33. And the way you're going to get that is you take the number of bonds that there is with the nitrogen and the oxygen. So in this case, you get 1, 2, 3, 4. And you count how many atoms are attached to the nitrogen. Because nitrogen has 3 things attached, or 3 atoms attached, what you're going to end up with is 4 bonds divided by 3, which gives you 1.33 bonds. And so the goal here is to understand this idea of resonance structures in terms of how they're going to go about talking about how many bonds they actually have. So most people would say, well, there's only 4 bonds. Why wouldn't it be 4? And the reason why it wouldn't be 4 is because you have other 2 existing ones. And you would have to draw the bracket. The bracket would indicate the overall excess charge over all of the atoms, and then you have to indicate double bond as is being put out there as well. Alright, another example is formate, or CHOO2 minus. In this specific case, the bonds between O and C are of the same length. However, if you're taking a look at how many effective bonds you actually have, you're going to have 3 bonds. So you have 3 bonds between the C, O, and you're going to have 2 atoms. And so in this specific case, you're getting 1.5. And the reason why we are using 3 here instead of, let's say, 4 bonds is because we're talking about the OC carbons are going to be exactly the same. So here in this case, you're going to get 1.5. Now, question here is which structure has the shortest bonds? And so let's take a look at NO or NO2 and NO3, and so you know these as nitrate and nitrite. And if you take a look at the actual structure itself, it has an excess negative charge, and if you count the electrons, it should end up being that way. So if you take a look at the bond order for this one is going to be a 1.5. And again, we're taking a look at how many bonds you actually have in this specific case divided by 2 atoms. So you're going to get 3 bonds here divided by 2 for the oxygen, which gives you that 1.5. Now in this specific case here, the bond order is going to be 1.33. And if you take a look at this, you divide 4, 1, 2, 3, 4 divided by 3 bonded, and then you're going to get that 1.33 bond order for that. So because the bond order is higher on the 1.55, this one is going to have the shorter bonds, as the effective number of bonds between NO is greater than that of the structure for NO3. So when we're talking about bond length and resonance structures, we really are talking about this idea of bond orders and also of length. And so even though both of them have double bonds, the answer here is that you're going to end up in that situation. All right, let's take a look at this one, and you can pause the video here to see if you can kind of understand this concept of bond length and bond energy. And so the question here is, which structure has the greatest bond energy? If you take a look at O2 as an example, right, we have to figure out the bond order. So go ahead and pause it right now and see if you can do it. All right, so if you go ahead and take a look at it, O2 has a bond order of 2, and again, the reason why you have 2 bonds here, you have 1 bond, sorry, and then you're going to be dividing that by how many atoms you actually have. So in this case, you have 1. So you have 2 bonds divided by 1. In this specific case, you have 3, and so the bond order is going to be 3 divided by 2, which is going to give you a 1.5. And so if you take a look at how many bonds you have divided by how many attached to the oxygen, you're getting 1.5. Now we compare the 2 and the 1.5, and because O2 has the greatest number of bond energy, it's going to have a greater number of bonds in that structure. So O2 is going to be definitely a lot more, has more energy than the O3 molecule. So a couple of things going on with bond energies and bond lengths. There's a couple of limitations to Lewis dot structures. The first one is going to be resonance structures. And so let's take a look at resonance as specifically the idea that many of the double bonds that are shown in the Lewis dot structures are actually not double bonds. They're going to be an average of these, the 1.5, the 1.3, and the 1.25. And this really kind of comes into play when you're looking at multiple structures. So the more of these structures you have, the more averages you're going to end up, just as we saw earlier with the nitrate. In some cases, resonance structures must be used to refine a Lewis dot structure in order to obtain accurate predictions about number of bonds, bond energy, and bond length. So normally what you use these Lewis dot models is for predictions about strength, energy, and also for bond lengths as well. So keep that in mind when you're looking at Lewis dot structures, that they do have a lot of limitations. And you know, when you end up with these situations where you have to move the bonds around, you're going to end up in places where you're going to have to effectively take those into consideration. Another one is when the octet rule fails when there are odd number of valence electrons. And so this is something you probably encounter with some of your problem sets where you're trying to do the Lewis dot structures, but then the octet rule doesn't really work. So when you sum up the valence electrons of all the atoms in the molecules and it's not an even number, the octet rule fails. And so remember how we talked about the octet rule is where you're going to have to need those 8 electrons, but when you're dealing with odd number electrons, then it becomes a little bit different. And so in this specific example, we're talking about nitrogen monoxide, or NO. So N has 5 valence electrons and O has 6. If you add them up, you get a total of 11 electrons. And so the problem here is that because you have that odd number electrons, you're going to have to deal with this specific case. So NO here has 2, 4, 6, 8, 2, 4, and then you got that 5 in there. So this one doesn't really, the nitrogen actually doesn't get the octet, but the reason why is because O kind of pulls on those electrons just to fill up the octet, and the nitrogen is okay being that N like that. So at that point, you're going to have to push the electrons here to make the octet. But even then, if you take a look at it, 2, 4, 6, 7, you only have 7 on the nitrogen. And then for oxygen is 2, 4, 6, 8. So this is the accepted Lewis dot in the fact that you actually have that oxygen getting that double bond. Another limitation of double bonds is incomplete octets and other issues. So the accepted Lewis dot structure for boron is that boron has the less ability to attract electrons. So when we're talking about electronegativity with, for example, fluorine, you always want to look carefully at which one is able to pull electrons and which one's able to attract. So boron does not really attract as much, and because of that, it doesn't fill up its octet. and it only has, because it only has 5 protons, it only brings in 5 electrons, and usually the formal charges, if you run them on here, they usually are going to work out. So boron's one of those exceptions to that rule. Another example here, so if you take a look at a boron, the formal charges on Lewis structure are unlikely for these two reasons. So if you take a look at doing a double bond just to satisfy boron, 2 4 6 8 2 4 6 8, the problem is the formal charges are not going to line up. So fluorine's going to have a positive 1, boron's going to have a -1, and then the other one's going to have a 0. And so we see a negative formal charge, but it should be on the fluorine, not on the boron. And so that's the reason why we go back to the incomplete octets. There are other issues about this, but usually if you take a look at the experiments for boron trifluoride, they say that the BF is less than it should be. And so this suggests that there is a resonance structure for boron, and usually is going to be greater than 1 in terms of the bond energy. All right, another situation with these is, and again, make sure you're kind of aware of this, is that you take a look at the electronegativity differences between boron and fluorine. You're talking about 2 and a 4, and this is basically meaning that this is a fairly ionic characteristic, and because of that difference, you're going to have this kind of potentially not having those electrons being shared. So if I were to write down any of these possibilities, none of these are 100% correct. So you have a possibility here, one, you have the double bond, double bond, double bond, or you even have an ionic character. So if you were to ask them that between which one is the dominant form, the incomplete one is going to be the dominant one, which is going to be this one right here. Now another situation where you kind of get a little bit different is going to be when expanded octets. And so here phosphorus 2 4 6 8 10, phosphorus here has 10 electrons, sulfur has another one, and your noble gas is xenon here. We don't really talk about it much, but these gases can actually go higher than the octet, and so sulfur is a very classic example of those. So if you ever find something with a sulfur and you're trying to put a fluoride in there, usually it's one of those exceptions to the rule. Alright guys, well, hopefully you enjoy this. Just in summary, just make sure you're aware that Lewis dot structures are generally very okay with certain types of elements, but for the most part it tends to have a lot of exceptions to the rule. So don't think of them as a hard and fast one. We have the expanded octets, we have elements that don't fill up their shells, and also we have resonance structures which have these multiple configurations where you have to fill in.